Alright, for the most important part in the radioactivity that you need to know before the prelim and the finals after is gonna be this one. So, firstly, I have here three different particles that you are all familiar with now. I'm sure you're familiar with it. I color it differently. I have three colors here. These ones are actually charged positive. This must be protons. All right. And here I'm putting 0. All right. And those are the neutrons. And around that bunch of subatomic particles, we can find these other particles. We call those electrons. All right. Just for a recall, you know that this location, or where you can find the protons and neutrons, is called the nucleus. Nucleus is not a physical entity. It is just a location where you can find these kind of subatomic particles. All right. Protons and neutrons can be found there, and that is also a reason why collectively protons and neutrons are being referred to as nucleons. All right, because they can be found in the nucleus. Okay. Now, another thing that you have to remember, and as a recall also about radioactivity, is the so-called alpha particles. These alpha particles are basically these ones. All right, these ones. All right. Usually, alpha particles are being emitted from the nucleus by heavy elements. All right. This one is lithium. It's in my drawing. It looks like a lithium because we have 3 protons. But alpha particles are usually given off or ejected from the nucleus of a very heavy particle. Imagine this is a heavy particle. 2 nucleus plus 2 protons will be ejected. All right, out. All right, they will be coming out like one particle, and that particle is called alpha particle. All right. Okay. So this one is something that we call the decay. All right, this phenomenon. All right, when the alpha particle leaves the nucleus, we can say that there is an alpha decay that just happened. All right. Now, say imagine we have a heavy nucleus. We call it maybe the nucleus of atom Y. And we have a number here as our convention. By the way, just for a recall, this is not a new thing to you. This is called nucleon number. In chemistry, they call this mass number. It's pretty the same. All right, it's just the what is it? The naming of these numbers. They are the same. Nucleon number, mass number. All right. The Z letter here represents the so-called proton number of how many protons are there in that atom. All right. In chemistry, you are calling this atomic number. All right. They are just the same. All right. Now, say imagine this one is atom Y with this nucleon number and with this proton number. After undergoing an alpha decay, all right. Of course, it will be releasing an alpha. All right. And an alpha, as you can see here, it looks like a helium nucleus. All right, containing two protons and 2 protons and 2 neutrons here. So that's why we have 4 and 2 here. All right, this is the number of nucleons. So we have 4, and there are 2 protons. So we have 2 here. All right, so this is alpha. All right, this is alpha, and therefore the resulting atom is gonna be whatever the original nucleon number is minus 4, and whatever the original atomic number is or proton number is minus 2, because these 4 and 2 went to the alpha particle already. All right, they have been ejected from the nucleus, meaning to say we will be having a different element after this atom underwent alpha decay, and this different element is 4 less than the nucleon number, or 2 less than the original proton number. All right. Now another thing as a recall also, You still remember I took, for example, I will be taking a nuclear neutron there, all right, neutron, or this yellow one. This can disintegrate, all right. It will be decaying to the possible product after the decay is going to be this purple, all right, and this blue one here, all right. This yellow one is a neutron, but following our notation here, we can just write this symbol as representing neutron. 0 proton number, it doesn't have a proton in it, and 1 here, all right. Okay, because it is a nucleon number, so it must have the number or the combined number of protons and neutron. So here we have 1. Now in this particular case, we have here a proton. We can write this using the same notation. Alright, in this case, it's going to be 1, 1. Alright, proton number, nucleon number. Now in the case of electron, it's going to be E, no proton and no neutron, so it's 0, and then you have here -1. Alright, you have here -1. Okay, so what we have here is a so-called beta particles. Actually, a beta particle, which is represented by the electron around here. Well, by the way, it's pretty the same. The characteristics of these electrons, the one that I discussed a while ago, and this electron from the nucleus, all right, the characteristics are different. The only the reason why they don't call this electron is because they want to make a distinction that this electron or a particle that has the same characteristics as that of the electron originated from the nucleus. Alright, they gave it a name, beta particle. Alright, later you will be seeing this one is only applicable to the beta negative decay. I will be explaining more about that later. Alright. Alright, so when we undergo a beta decay, alright, as a recall of the previous lessons that we had before, if you originally have a heavy element, alright, or heavy atom with this notation, alright, if it emits a beta particle, or this one, alright, it will be ending up as having the same number of nucleons, or the same nucleon number. Why? Because you see, we can think of it as the neutron is gone, but where it was turned into a proton and a beta particle. So the same thing. It's going to be like A minus 1, because minus 1 electron, 1 neutron, but you have to add 1 proton again. So it's just cancel. The effect just cancel each other. All right. So this remains the same. All right, the same number of nucleon. Alright, or nucleon number or mass number. However, when it comes to the proton number or atomic number, it's going to be whatever the original proton number is. You have to add 1. Alright, the reason is, okay, when the neutron decayed into these two, alright, one of these two is a proton. So this one should have an increase of 1 proton. Since the number of protons change, so this is going to be a different element or a different atom. So we can say that this one is an atom X, just to just to represent that this is different from the original one anymore. Yeah, okay. After releasing a beta particle, all right. Whenever an object release an alpha or undergo beta decay, the resulting atom is going to be different from the original one. Just like the one represented by X's here. Okay? Remember these notations, guys, because you will be needing this. Alright? Okay. Imagine I have francium. Alright? This francium, let's assume there are 221 nucleons in it. Alright? And after some time, imagine we observe that the francium this exists in one particular area. Alright, after some time, there wasn't any other particle there. Alright, you can imagine it like that. But after some time, there's already this. Maybe we found a bismuth. Alright, with this 209, alright, as its nucleon number. Okay, so what happens here is there should be a decay. Alright, the francium has decayed into a bismuth. Alright, the one that I presented to you a while ago, we can either have the alpha decay and then we have the beta decay. Considering that francium, the atomic number of this one is 87. For the bismuth is 83. Okay, it can't be just an alpha decay here. It can be also a beta decay here. This must be a series of decays. Some of the decays may be alpha, some of the decays may be beta. Alright, now we can try to see what are the possibilities. There are many ways on how this is going to happen, but one possible is this one. Maybe we start with this. Alright, with the francium 221. Alright, with 87, that's its atomic number or the proton number. If it undergoes a alpha decay, so this one will be changed into 221 minus 4. Alright, because an alpha has 4 nucleon number. Alright, so this one here is going to be 85 and this one is 217. I put an X here because this should be another element or another atom. Alright, the number of protons defines the atom. Alright, for if the number of proton is 87, then it must be francium. Alright, if the number of protons is 83, then it's not francium anymore, it's bismuth. Alright, the same with 85. This is not francium, this is not bismuth also. Alright, now from here, okay, let's copy that. Alright, maybe it also underwent alpha decay, and after releasing an alpha from the nucleus, so what will happen is that we will be having a new atom with 83 atomic number or proton number and 213 nucleon number. You see, remember, whenever you have an alpha decay, this one is minus 4 and this one is minus 2. Alright, just like what happened here. Alright, now I think we can again do this one. So imagine we have 213 and 83. I just copied this. Alright, if it release alpha again, then what we'll be having in the end is gonna be another atom different from this. Alright, the reason is this one has already changed again. Alright, it goes down by 2 because of the alpha took 2 protons with it. Alright, so from 83 this one becomes 81. Alright, this one 213, it becomes 209. Alright, because you guys, you can see in our notation a while ago, this should be minus 4 whenever there is an alpha decay. Okay, now as you can see, we already have here 209. Alright, we already have here 209. Alright, and the one that we observe, for example, is already 209 there. Okay, is there a decay that doesn't affect the nucleon number? Yes, there is. It's the beta. Alright, and the effect of the beta, this one unchanged, but this one will be increased by 1. Alright, based from our notation a while ago. Alright, just to show it to you, it's gonna be this. So originally I just copied this part to 20981. If this undergoes or underwent a beta decay, then what will happen is that we will be producing a new atom with the same atomic same nucleon number but different atomic number, or one more than the previous atomic number. So this one is 82. Alright, so this is after one beta decay. So our target is bismuth. and bismuth is 83. We have here 82 now. So in order for this to happen, there has to be another beta decay. Alright? Okay, if that's so, then what we will be having in the end is 83 here as atomic number, and here is still 209, because in beta decay the number of nucleons are actually unaffected. Okay, and this one is now this thing. Alright, what we have here is the result, alright, from our observation, alright, from our what is this situation a while ago. Okay, so from francium, with this particular specific number of nucleon number and proton number going to this one possible thing that happened was it underwent series of decays. Like here we have 1, 2, 3, 4, 5, so 5 decays, 3 alphas and 2 betas. Okay, even if you change this, for example, you start with a beta, then followed by an alpha, and then a beta again, and then 2 alphas, you will be ending the at the same atom. Alright, the same bismuth atom here.